Hey everyone, welcome back. Today we're moving on to chapter 17 in our textbook on static electricity, but this time we're going to be looking at it through the lens of potential energy and potential. The big difference here is that we're going to be looking at things that are scalar quantities instead of vector quantities, which you should know makes your life a lot easier. It also segues beautifully into what we're really going to try to get to here, which is the flow of moving charges, which we also call, that's right, electricity. So that's where this is all heading. The thing about trying to picture electrical static forces with energy, static electricity with energy and potential is that it's hard to visualize. So what I would like to do is to go through a chart where we compare things in the gravitational world to the electrical world. Okay? So what we're going to end up doing is about 2 pages of notes on a big chart. You're going to basically draw a line down the middle of your paper. And on one side, we're going to talk about gravity. And on the other, we'll make the connection to electricity. Got it? So you got a nice clean sheet of paper in front of you. You have taken a ruler, drawn a line straight down the middle of that. And on the left-hand side, I'd like you to put gravity. And on the right, electric. All right, let's begin. So this first part's going to be review. So relax. Let it wash over you as you take nice, clean, beautiful notes. When we talk about the force of gravity between two objects, M1 and M2, the formula that we would end up using is going to be Newton's law of gravity. F equals gm1m2 over r squared. Which one of those objects experiences a greater force? Yeah, nice job. Good. Neither, right? They both experience the same force. Now, the field strength caused by one of those charges can be calculated as gm over r squared. Now, this is where it gets a little confusing. For field strength, I could utilize the symbol A, or I could, on Earth, we use a lowercase g. So field strength would just be gm over r squared. All right. Now, if I want to find the sum of the forces on a mass, I would just multiply the mass times the field strength. Now, we also call that the weight. All right, cool. And just to sort of throw this out there, if we're on Earth, then if we have a mass, we always measure distances r to the center of the mass. Always. It's just the way it is. Okay. Now, in the last unit, when it comes to electrical charges and forces, we utilized Coulombs Law. Now, Coulombs Law states that the force of electrical attraction is K Q1 Q2 over r squared. And as a quick aside, K is a constant that is equal to 1 over 4 pi epsilon naught. It's substituting in one constant for another. That's all. And we know that that value for K is 9 times 10 to the 9th. It's a bit of foreshadowing for later in the year. Now, when we talk about electric field strength, we utilize the symbol E. Capital E is KQ over r squared. And if I want to find the sum of the forces on an object, it's not related to the mass, but instead to the charge times the field strength. Yeah. All right. I could, just to continue with this analogy here, let's say I had a solid sphere with charges on the outside. Let's say that there's a lack of electrons on this sphere, leaving it with a positive charge. When I would do calculations for this, R is still actually going to be measured from center to center. Okay. Now, the thing about everything we did in the last unit is that these quantities, electric forces and electric fields, are vectors. As such, we had to always take into consideration the direction, and often we even had to take into consideration the angles. Now, that was a pain in the neck, wasn't it? Every single problem, those two that were on the test that you had to work out, were huge one-page problems. And there has to be an easier way. And there is. Just like when we were studying motion, we segued from mechanics and basic kinematics into energy. We can do the same thing when it comes to electrical. Now, let's return to gravity. So the potential energy due to gravity, I'm going to write it as PE for a moment. PE with a subscript G. We actually, in the AP physics world, utilize the symbol capital U. You'll see this on the AP test. In the textbook, we'll often use PE, but the AP often will use U. I'll use both. Okay? Now, one of the simplest formulas from all of last year is U equals mgh. Nice. And up above, I already defined G as being capital G M over R squared times H. Now, H is really a measurement of R. So I can take that, cross it off, and I end up with a formula that is G M1 M2 over R. I now have a way to calculate the potential energy of an object in a gravitational field. Yeah, we didn't really utilize this formula last year, but I think you can handle it. Now, what's the connection with electrical energy? Well, I'm going to utilize PE electrical. But you know what? We're often going to use a U with a subscript capital E for that. Now, if gravitational potential energy is mass times gravity times distance, then electrical potential energy, the equivalent to mass in the electrical world, is charge. Field is E, and often we use a D to represent distance when we talk about electrical distances. Why is it not an R? Honestly, they're equivalent. I think it's D because we're often going to look at distances between capacitor plates, and we use R with gravity because we're usually talking about radiuses of planets orbiting. Now, if I keep going and clean this up a little bit, just like I did in the previous section, so UE is going to be Q, I'll call it Q1, K Q2 over R squared times D. The D and the R, because again, they're measurements of distances, are going to cancel out. And I'm going to end up with a formula for electric potential energy caused by a charge. So there's the bell. I think I'll take a moment and edit this out. It's depressing, isn't it? And we're back. So before I move on, I got to throw out that we just talked about two new formulas. The potential energy of a charge placed in an electric field would be equal to QED. And we could also, if we had just two charges, find the potential energy associated with those two charges. All right. Hey, cool. We got some new formulas. But they're not the ones that are most useful. There's another way that we can talk about potential energy in electrical systems. But you know what? We're first going to talk about gravity. Now, here's a term I did not use often last year. Here it goes. Ready? If potential energy due to gravity is mgh. Let me ask you, what if there's no m there? What if m was not present? And right now you're thinking, what? Yeah, I know. Usually I'm giving this lecture in front of the board. But play along. What if there was no mass there? And by there, I mean in the gravitational field. So if I were to go ahead and draw a picture, let's say that we are standing on the surface of the earth. Okay. And you look out and there's trees, there's birds flying around, and you're standing in this gravitational field. That field would be pointing straight down towards the center of the earth. Now, if I place a mass in that field, you all know, I know you know, that that mass has potential energy. But what if the mass wasn't there? What if we just talked about that point in space? Right here, right like beside it, with no mass there. Do you know what that spot has? That spot does not have potential energy. This spot has potential. Just like some of you. No, I'm just kidding. This has potential. Not potential energy. It has potential. Now, let's take a look at our formula. If we look at UG equals mgh, but we get rid of the m, it goes from potential energy to potential. Have I said that enough times yet? I'll say it some more. What we end up with is the potential is going to be the field strength times the distance, or GH. Now, last year we didn't really talk about that. It doesn't have a great symbol. In fact, sometimes we just call it pot, but then everybody snickers, so that doesn't work great. So instead, I will sometimes refer to this idea of gravitational potential as goltage. Goltage is equal to the field strength times the distance. Ooh, let's write that out. Yeah, goltage. Goltage. You know what has goltage? This spot right here has goltage because there's a gravitational field with no mass in it. But now, if there's a mass there, what does this mass have? That's right, it now has potential energy. No mass, this spot has potential. I put a mass there, it now has potential energy. Huh? Yeah, that's not so bad. I think you get that. So what the heck's that have to do with electrical stuff? Well, let's take a look. If we say that electric potential energy is the charge times the field strength times D, what if there's no charge there? Yeah, go ahead, write it down. Let's draw a picture. Instead of gravitational field lines, what I'd like to look at instead are electric field lines. And it is very easy to create a uniform electric field between two charged plates. and it's easy to get plates to charge. Let's leave it at that. So if I have a positively charged plate and a negatively charged plate, I would end up with a field line that goes from top to bottom. And the field strength is actually uniform between those two plates. It doesn't get stronger the closer you get to one plate or the other. The field actually stays uniform. Now, if I take a positive charge and I place it there, right here, it now has potential energy. But what about that point in space? The tablet's having trouble keeping up with me. You know why? Because this stuff's hard, guys. This spot right there, that spot has potential. There doesn't have to be something there in order for it to have potential. It doesn't have potential energy. It has potential. So let's go back to our formula. If UE equals QED, if we cancel out the charge, then what I'm left with is the potential equals ED. Now, the thing is, we don't call this pot. It actually has a name. It's actually called the voltage, named after Alessandro Volta. Now, the voltage would be equal to ED, and because it's a term that we use all the time, unlike Goltage, it actually does have its own symbol, and that symbol is going to be a capital V. So write that in. Capital V equals ED. Bam! Electric potential. Voltage is equal to Ed. Now, it's unfortunate that we don't have anybody with the name Ed in this class, because they would have a lot of potential. So voltage equals Ed. We'll be right back. They're making us listen to this now. It's brutal. And we're back. All right, so if voltage can be defined as the electric field times the distance, it is often rewritten as a definition for the electric field. So we can write that as the electric field could be the electric potential divided by the displacement. So now we have two new formulas. Now, what I would like to do is to do a quick check on the units. What are the units equal to? Well, when we talk about electric field, so maybe I'll write units here. If voltage equals ED, electric field is measured in newtons per coulomb. Distance is measured in Newton meters. Now, who knows what a Newton meter is equal to? Force times distance is work. Work is a measurement of energy. Energy is measured in joules per. Energy is measured in joules. So joules per coulomb is a volt. Now, this is one of those cases where the term voltage and the units, volts, both start with the letter V. Yep, it's true. It's just the way it is. Okay, so a volt is a measurement of a joules per coulomb. Just to complete our notes here, if we were to take a look at gravity, What would this voltage be measured in? Well, if voltage is going to be gravitational field, what are some other units that we could use for field strength? Ah, that's right, newtons per kilogram. So a newton times a meter is going to give us joules, and what we'll end up with for units would be joules per kilogram. Now, we got kind of stuck in the weeds there for a bit. Voltage is a measurement of gravitational potential. And basically, if I put a mass there with a mass m, it will have potential energy, right? But this spot in space just has joules per kilogram that's placed there. When we talk about charges in a field, that point in space in that electric field has potential. And if I place a charge in that spot, it would then have potential energy. And what is that potential energy going to convert into? That's right, kinetic energy. Yeah, motion. Good. And we'll get into like what that means later. But